Alright, here we are in our first lesson on Unit 3, Generating Equivalent Expressions, and this is Part 1. We're going to start off with some vocabulary. Now these are going to be kind of lengthy explanations, so please in your math journal go ahead and condense them down using your own words to summarize what these represent. First off, we're going to talk about variable. A variable is a symbol such as a letter that represents a number. It is a placeholder for that number. Now a variable is actually quite a simple idea. It is a placeholder or a blank in an expression or an equation where a number can be inserted. A variable holds a place for a single number throughout all calculations done with a variable. It does not vary, which means variable is kind of a misnomer. It is the user of the variable who has the ultimate power to change or vary what the number is that is inserted, as he or she desires. The power to vary rests in the will of us, not the variable itself. Numerical expression. For our purposes in middle school, a numerical expression is a number, or it is any combinations of sums, differences, products, or divisions of numbers that evaluate to a single number. Statements such as 3 plus or 3 divided are not numerical expressions because neither represent a point on a number line. You obviously have to finish the statement 3 plus some number or 3 divided by some number in order to get that single value that can be placed on a number line. The value of a numerical expression is the value of the number found by evaluating that expression. So simplifying it down to one value is that value of a numerical expression. For example, 1/3 times the quantity of 2 plus 4 minus 7 is a numerical expression and its value is -5. An expression, for our purposes, is a numerical expression, or it is a result of replacing all or some of the numbers in a numerical expression with variables. There are two ways to build expressions. We can start out with a numerical expression such as 1/3 times the quantity of 2 plus 4 minus 7 and replace some of the numbers with letters to get 1/3 times the quantity of x plus y minus z. We can build such expressions from scratch, as in x plus x times the quantity of y minus z, and note that if numbers were placed in the expression for the variables x, y, and z, the result would be a numerical expression. Equivalent expressions. For our purposes, two expressions are equivalent if both expressions evaluate to the same number for every substitution of numbers into all of the letters in both expressions. This description becomes clearer through lots of examples and linking to the associative, commutative, and distributive properties. An expression in expanded form. For our purposes, an expression that is written as sums or differences of products whose factors are numbers, variables, or variables raised to a whole number power is said to be in expanded form. A single number, variable, or a single product of numbers and or variables is also considered to be in expanded form. The opposite of that would be an expression in standard form. An expression that is in expanded form, where all like terms have been collected, is said to be in standard form. An expression in standard form is the equivalent of what we traditionally refer to as a simplified expression. Another way you can equate this is thinking about fractions. We can name several fractions that would indicate a single point on a number line, yet typically we are told to reduce our fractions to simplest terms, meaning that we find the least common denominator. This is the same effect that we have on expressions in algebra. All right, let's take a look at the opening exercise on your lesson worksheet. Pretend that you have an envelope that contains a number of triangles and quadrilaterals. As stated on your lesson worksheet, we will let T represent the number of triangles and Q will represent the number of quadrilaterals. We're going to write an expression using T and Q that represents the total number of sides in your envelope. Explain what the terms in your expression represent. First of all, let's review. How many sides does a triangle have, and how many sides does a quadrilateral have? Well, hopefully you said 3 and 4. So therefore, our expression should be 3t plus 4q, or 3 times t plus 4 times q. Since triangles have 3 sides, so there will be 3 sides for each triangle in the envelope. This is represented by 3 times t. Quadrilaterals have 4 sides, so there will be 4 sides for each quadrilateral in the envelope. This is represented by 4q, or 4 times q. The total number of sides will be the number of triangle sides and the number of quadrilateral sides added together. So let's continue to pretend that you and your table partner, if you were at school, have the same number of triangles and quadrilaterals in your envelopes. Write an expression that represents the total number of sides that you and your partner have. If possible, write more than one expression to represent this total. So you could have come up with 3t plus 4q plus 3t plus 4q, or you could have done 2 times the quantity of 3t plus 4q, or even still, you could do 6t plus 8q. Or you might have some other way of showing this. So are these expressions equivalent? Well, they are. You can either add all the triangles and all the quadrilaterals separately, you can combine like terms, or you can also double your own number of triangles and quadrilaterals since there are 2 of you. Pretend that everyone in the class, and let's say our class has 28 students, has the same envelope that contains the same number of triangles and quadrilaterals. Write an expression that represents the total number of sides in the room. Well, the easiest way to probably represent this is 28 times the quantity of 3t plus 4q. But what other variations of the expression can you think of? Well, you can also represent it as 84t plus 112q. Or by multiplying 28 times 3 and 28 times 4. So let's say you open your envelope to find that there are 4 triangles and 2 quadrilaterals. Use the given values of t and q in your expression from part A to determine the number of sides that should be found in your envelope. You should have something that looks like this. We always start with our original expression, then we show that what values we are substituting in for our variables, and then we use the order of operations to simplify to a single value. In this case, 3 times 4 is 12, 4 times 2 is 8, and 12 plus 8 is 20. So therefore, there should be 20 sides in your envelope. Use the same values for t and q and your expression from part B to determine the number of sides that should be contained in your envelope and your partner's envelope combined. Well, there's several ways you could have done this, depending on which variation you use. It would be 2 times the quantity of 3t plus 4q, or you could say 3t plus 4q plus 3t plus 4q, or you could have 6t plus 8q, or maybe something equivalent. But again, we always start with the original expression. Then our second step is substituting our values in for our variables. And then after that is just using the order of operations to get to a single value. In this case, it is 40. So we have a combined total of 40 sides. So use the same values for t and q and your expressions from part C to determine the number of sides that should be contained in all of the envelopes combined in class. Now this particular example is a sample response for a class of 12. However, you should have the same process for using 28 or whatever number you used for our class. So instead of coming up with 240, if you did use 28, you would have a total of 560. So what do you notice about the various expressions in parts E and F? Well, the expressions in part E are all equivalent because they evaluate to the same number, which is 40. The expressions in part F are all equivalent because they evaluate to the same number, which is 240, or in our case, 560. The expressions themselves all involve the expression 3t plus 4q in different ways. In part E, 3t plus 3t is equivalent to 6t, and 4q plus 4q is equivalent to 8q. There appears to be several relationships among the representations involving the commutative, associative, and distributive properties. So let's go to example 1 on your lesson worksheet. For part A, we're going to rewrite 5x plus 3x and 5x minus 3x by combining like terms. First, we're going to write the original expressions and expand each term using addition. What are the new expressions equivalent to? Well, for 5x plus 3x, remembering that 5 times x is repeated addition of x's 5 times, and 3 times x is repeated addition of x's 3 times. Well, if we have 5 x's and we add an additional 3x, then we have a total of 8 x's, or 8x. Conversely, if we have 5x minus 3x, we would show 5 x's being repeatedly added, but then we would take away 3 of those x's, and that would leave us with a difference of 2, or 2 times x. Because both terms have a common factor of x, we can also use the distributive property to create an equivalent expression. So in this case, 5x plus 3x, we can factor out an x and put it on the outside of the parentheses, and what's left over is 5 plus 3. Well, when we simplify that using the order of operations, 5 plus 3 is 8, and 8 times x is 8x. For the other operation of subtraction, we can factor out an x, and what we have left is 5 minus 3. Well, 5 minus 3 simplifies to 2, and 2 times x is 2x. So write the equations 5x plus 3x equals 8x, and 5x minus 3x equals 2x. Try substituting different numbers for x to see if you can come up with a false statement. Here is an example. So let's say x is 2. Then we would have 5 times 2 plus 3 times 2 equals 8 times 2, which can be simplified to 10 plus 6 equals 16, and lastly, 16 is equal to 16. So try it on your own and see if you can come up with an equation that is not equal. All right, so you should have noticed that you can't find a number that will create a false statement, that both of these expressions are equivalent. Simplifying 5x plus 3x equals 8x is known as collecting like terms. For part B, find the sum of 2x plus 1 and 5x. In its expanded form, we would have x plus 1, representing 2x plus 1, and again, 5 x's. In this case, 2x plus 5 x's would be 7x plus 1. But let's do this using the properties of operations. So our original expression is the quantity of 2x plus 1 plus 5x. Now, by using associative property, we can regroup the 1 and the 5x. Using commutative property, we can change the places of 5x and 1, which means that now we can group our like terms of 2x plus 5x. By using distributive property or combining like terms, we can factor out an x and add 2 plus 5. And that gets us to 7x plus 1, which is an equivalent expression to the given problem. So therefore, the quantity of 2x plus 1 plus 5x is equal to 7x plus 1. Why did we use the associative and commutative properties of addition? Well, we reordered the terms in the expression to group together like terms so that they could be combined. Did the use of these properties change the value of the expression, and how do you know? Well, the properties did not change the value of the expression because each equivalent expression includes the same terms as the original expression, just in a different order and grouping. If a sequence of terms is being added, the any order, any grouping property allows us to add those terms in any order by grouping them together in any way. So how can we confirm that the expression, the quantity of 2x plus 1 plus 5x, and 7x plus 1 are equivalent expressions? Well, when a number is substituted for the x in both expressions, they both should yield equal results. So go ahead at this time, pick a number to substitute into each of the expressions, the quantity of 5x plus 1 plus 2x, and 7x plus 1, to check that they yield the same results. When you have done this a couple of times, check your answers. So in this case, the example they used was x equals 3. Notice what happens when you plug in x equals 3. It simplifies to a value of 22. When you plug in x is equal to 3, again it simplifies to an equation or expression that is equal to 22. Therefore, we get the same result. The expressions both evaluate to 22, however, this is only one possible value of x. As a challenge, see if you can find any value of x where this would not be true. So let's look at part C. What prevents us from using any order, any grouping in part C, and what can we do about it? Well, the second expression, 5a minus 3, involves subtraction, which is not commutative or associative. However, subtracting a number x can be written as adding the opposite of that number. So by changing subtraction to addition, we can use any order and any grouping. So let's take a look at part C. Our original expression, the quantity of negative 3a minus 2 plus the quantity of 5a minus 3, can be written as the second grouping, 5a plus a negative 3, using adding the opposite or the additive inverse. Now we can use any order, any grouping to combine our like terms, or at least put them in the same vicinity as each other, and combining our constants. So once we do that, combining like terms, we get 2a plus a negative 1. And last, we know that plus a negative 1 can be written as 2a minus 1 because adding the inverse is also known as subtracting. So what was the only difference between this problem and those involving all addition? Well, first we had to rewrite subtraction as addition. Then the problem was just like everything else that we've done. All right, let's take a look at example 2. Find the product of 2x and 3. Well, when we do this, 2x 3 times means that we have 2x plus 2x plus 2x. If that's the case, then that would equal 6x. So we can use the associative property of multiplication, which is any grouping, by grouping the x and the 3 instead of the 2 and the x. Now we can use the commutative property to switch the order of x and 3. And lastly, because 2 and 3 are next to each other, 2 times 3 is 6, using multiplication, and we're left with an x. So why did we use the associative and commutative properties of multiplication? Well, we reordered the factors to group together the numbers so that they could be multiplied. Did the use of these properties change the value of the expression, and how do you know? Well, the properties do not change the value of the expression because each equivalent expression includes the same factors as the original expression, just in a different order or grouping. If a product of factors is being multiplied, the any order, any grouping property allows us to multiply those factors in any order by grouping them together in any way. All right, let's take a look at example 3. Using any order, any grouping to find the equivalent expressions, let's start with A, 3 times 2x. Well, we know that we can group 3 times 2 because we can multiply those numbers, and we end up with 6 times x, or 6x. Try to find an example or a value for x where 3 times 2x equals 6x. Try a variety of positive and negative numbers. Use the order of operations. First multiply by 2, then multiply by 3. Go ahead and try this a couple times before continuing. All right. Next we're going to complete parts B through E. Continue the video to check your answers. All right, you should have B through E completed, and this is what you should have. Make sure to pay attention to the process. Remember that the process in algebra is very important to prove the steps that you are taking to simplify expressions. If you have any questions, now is the time to write them in the margin so you can bring them to class. All right, continuing on. For part F, Alexander says that 3x plus 4y is equivalent to 3 times 4 plus x times y because of any order, any grouping. Is he correct? Why or why not? Well, he's incorrect because the expressions are not equivalent. Because if, for example, we let x equals -2 and y equals -3, we would get the following. Notice what happens when we substitute in -2 and -3. In the original expression, we would end up with -6 plus -12, which is -18. In the supposed equivalent expression, 3 times 4 is 12, and -2 times -3 is +6, which results in 18. Well, -18 obviously isn't equal to 18, so these expressions cannot be equivalent. So what can be concluded as a result of part F? Well, any order, any grouping cannot be used to mix multiplication with addition. Numbers and letters that are factors within a given term must remain factors within that term. All right, let's wrap it up. So we found that we can use any order, any grouping of terms in a sum or of factors in a product. Why? Well, addition and multiplication are both associative and commutative, and these properties only change the order and grouping of terms in a sum or factors in a product without affecting the value of the expression. Can we use any order, any grouping when subtracting expressions? We can use any order, any grouping after rewriting subtraction as a sum of a number and the additive inverse of that number, so that the expression becomes a sum. Why can't we use any order, any grouping in addition and multiplication at the same time? Well, multiplication must be completed before addition in the order of operations. If you mix the operations, you change the value of the expression. All right, we'll see you in class.